Our next speaker used to be a pants model for Everlane. Please welcome Walker.
When I first emailed Jared my fun fact like 3 months ago, I didn't realize he was going to be announcing it on stage while I was under a spotlight. But I guess that's just a rookie mistake because this is my first our conference. Last talk of the day, so it will be either a blessing or a curse that I'm standing between everyone here and a happy hour, so we will see. My name is Walker Harrison. I work for the Yankees in their front office as a quantitative analyst. Usually when I describe that role, I liken myself to the Jonah Hill character from Moneyball, if you've seen it. Basically, I'm the statistics guy who's helping suck all the fun out of baseball. So I'm sorry about that. If anyone wants to talk about getting into sports or getting into baseball, please come up to me after this talk. Something I do a lot of at work is I write R, and then sometimes I come home and I continue to write R. I go on little side quests. Usually they have to do with some facet of living in New York City, and sometimes I'll try to analyze a non-baseball sport, often the NFL. And in this case, some research I did earlier in the year actually got some traction on Twitter and got some people yelling at me on Twitter, which is the ultimate sign that you have something to say. So today I'm going to present that to you. And it's basically how we can use R to simulate playoff overtime to actually determine the optimal strategy. To determine if you win the coin toss in overtime, do you want to kick the ball or do you want to receive the ball? Okay, I know that we're in America, so maybe this is all part of our collective knowledge, but we are going to go over a little bit of how football works. Teams can score field goals and get 3 points. Teams can also score touchdowns, and that would be broken into kicking the extra point and getting 7 points, or converting a 2-point attempt for 8 points, or you could fail at either and end up with only 6 points. So that's just a quick overview of scoring. What is overtime? Overtime is basically additional gameplay that you have to use to determine a winner if an NFL game is in fact tied after 4 quarters. In the regular season, they cap it at 10 minutes, so if you play 10 minutes and it's still tied, then it's just a tie. But playoff games require winners, so playoff overtime just persists until someone wins. There have been various iterations of overtime over the years, and we'll sort of get into that a little bit. But it's always started with a coin toss, and the referee will toss a coin, the visiting team will call heads or tails, and if you win the coin toss, you get to choose to either receive the ball or kick the ball. And for decades, this was an easy choice. You wanted to keep the ball, you wanted to receive it, but a recent rule change has made that sort of a more nuanced decision and inspired this analysis in the first place. Okay, so we'll do a quick history of overtime. It started out way back when as sudden death, which just means that whoever scores first wins. And it was pretty obvious what to do if you won the coin toss in this situation. You want the ball first, you want the first crack at winning, and indeed 60% of teams that possess the ball first actually won. And then in 2010, there was a particularly painful playoff game for the Minnesota Vikings where their opponent kicked a field goal on the first possession of overtime, without the Vikings even getting a chance to possess the ball. And people wondered, well, maybe we should change these rules so that each team actually gets to have the ball. So the NFL stepped in and they modified overtime so that both teams get the ball, unless the first team scores a touchdown. So sudden death rules still applied in the case that the first team with the ball scored a touchdown. So there still wasn't quite a fair proposition for the team that didn't win the coin toss, because 55% of teams that won the coin toss and received the ball still actually won the game. It was a little bit more fair, but not quite fair. And then 2022 rolled around, and there was another sort of high-profile playoff game where a team, the Buffalo Bills, lost without even getting a chance to possess the ball because the Chiefs scored a touchdown immediately. And again, there was a movement within the NFL, I think, and also outside to make the rules a little bit more fair. Which brings us to modern overtime, where both teams are guaranteed to possess the ball. We don't know what percent of teams who get the ball first actually win, because this rule was only triggered for the first time this past Super Bowl, so 4 or 5 months ago. And in that Super Bowl, if you were one of the 125 million people watching, which was a record for the event, the The 49ers won the coin toss. They chose to receive the ball first. They scored a field goal, and then the Chiefs, who are guaranteed a possession now, responded with a touchdown to win the game. And the reactions to this were pretty extreme and pretty one-sided, whether it was ESPN pundits or like armchair analysts or even players. Most people thought that the 49ers had basically screwed up this decision, that choosing to receive the ball first allowed the Chiefs to know how many points they needed to tie or win the game, and that they basically forfeited a lot of win probability with their decision. But was it actually the wrong decision? And that's what I kind of set out to figure out using simulation. This was a situation that was pretty ripe for hindsight bias. This was the only example of a game like this ever. We knew what the 49ers had done, and we knew that it didn't work out. So it was very possible that there was a lot of sort of recency and hindsight bias driving this reaction to the 49ers decision. So what can we actually do? We need to determine the optimal overtime strategy. And basically the question is, should teams that win the coin toss actually choose to kick the ball off and receive the ball second, or should they choose to have the ball first? And what this comes down to basically is a debate about what advantage is greater. The people that were critical of the 49ers were basically saying that the information of going second and knowing how many points you needed to score to tie or win the game sort of trumped all. While we also have to consider the value of having the first and the third possession, because the third possession, should the game still be tied, is when sudden death kicks in, and there's an obvious advantage there. So the main debate is weighing those two things. So how do we do this? The basic setup is to try to create a sequence of discrete states, which is a go-to methodology in my world, in the sports world, and I'm sure in all sorts of other walks of life, is if we can simplify our situation down into these sort of discrete states that we can pass through and end up potentially at some sort of terminal state. So let's build that discrete state model. So just so we're all on the same page, anything that's red is going to be the receiving team. Anything that's blue is going to be the kicking team. And what we really care about is how many points are you scoring and how often is that going to happen. So we start with the first possession of overtime, and basically 4 things can happen. You can score 0 points, you can score a field goal for 3 points, or you can score a touchdown, which would yield 6 or 7 points. And each one of these situations sort of branches out into a second node for the kicking team, and within those nodes, there will be individual paths for the number of points that they might score. So starting with the top node for the receiving team, they might score 3 or 6 points in response to the first team not scoring at all, and then that would naturally end up at them winning. If the first team doesn't score and the second team doesn't score, you end up in a sudden death situation. I won't walk you through every single one of these paths. You can trust that I sort of explore the entire space here. And what you get here, well, first of all, just to note, there's no defensive touchdown showed here, mostly for simplicity. If you're wondering, about 1% of possessions end in a defensive touchdown, which would automatically be a loss. So if you gave up a defensive touchdown, you'd go straight there. Not shown for simplicity. So basically what you end up with is this, this discrete graph that's actually not too complicated. It gets a little bit hairy in here with all these overlapping paths. But overall, in terms of taking something that's pretty complex, NFL football, and boiling it down to a series of these discrete states, it's not that bad. There's 8 nodes, and 2 of them are terminal. So we really only have to figure out how to get from each one of these nodes to the next. So how are we going to do that? Well, we need to basically determine transition probabilities for each one of these. And that starts with getting play-by-play data from the NFL FastR package. Want to shout out Ben Baldwin and Sebastian Carl for creating that package. Really easy to quickly get 25 years of every play since 1999 of all NFL plays. As is the case for most of my stuff, when I'm writing a blog post or doing some analysis, I'm very much standing on the shoulders of people that have put together some really good packages. So I wanted to give them a shout out. OK, so back to the main problem. How do we get these transition probabilities? Well, a lot of them we can actually estimate empirically. So if you go back to the actual graph, a team trying to score in a tie game here or here is not really foreign territory in the NFL. We can probably just take empirical scoring rates and plug them in there. We have plenty of situations where teams were receiving the ball after a kickoff, or teams were receiving the ball after the first team didn't score, that we can probably just approximate these probabilities by plugging in some empirical distributions. And then we also, like I said, the NFL played sudden death overtime for many decades, so we can probably just plug in sudden death probabilities into this node. So while we started with just 6 nodes to figure out, we can just plug in empirical probabilities for 3 of them. The other three we have to simulate because they are happening in a context that hasn't been played enough in NFL football. Like I said, this is a new rule, so there's not going to be a lot of instances of a team being down a touchdown and needing to score just to extend the game. And there's not going to be that many instances of needing a field goal to extend the game without any regard for the clock. So we can get halfway there with empirical data, but we're going to need to simulate to sort of finish up. So we can plug in transition probabilities for those empirical ones, and then these 3 are still what we need to figure out. OK, so how are we going to actually simulate these possessions under these unusual constraints? Well, we have our play-by-play data, right? And basically, we need to create a sample of plays from teams in game situations where we know they're trying to score. So what that basically means is let's get rid of plays from games with huge score differentials or not that much time left on the clock, because we think that, for example, a team with the ball up by 30 points or a team trying to tie the game with a minute left and no timeouts doesn't really sort of reflect the context that we're trying to recreate. So that starts us off with a sample, and then we can buff that sample up a little bit by duplicating plays with slight modifications. What I mean by that is if you're looking for a 4th and 12 from your own 31-yard line, even though we have 25 years of data, we might not actually have that many plays that actually make sense in that context. So what we can do is we can take plays that are pretty similar and modify them just to add to our sample to make sure we don't get sort of stuck in the same sequences over and over again. Once we have our sample, all you really need to do is initiate a drive with some sort of random play after a kickoff. And then we will seed each next play with the ending conditions of the previous play. So we have an initial play. We take how that play ended, and we look at our sample for plays that began like that. And in that manner, we can basically just chain together plays one after the other. So for example, if you have a 2-yard run to start your drive on 1st and 10, suddenly you're looking for 2nd and 8 plays. We're going to add some constraints to actually make this make sense in this context. So we're not going to let teams punt if they need to score. We're not going to let teams that are down a touchdown go for field goals, because those would result in automatic losses. From there, though, it's just it's rinse and repeat, right? You just keep on adding plays until either a team scores or they run out of downs. And it wouldn't be a good R conference talk if there wasn't some actual R in it, so I'm going to throw some up here. This is a pared down version of this function. Anyone that's ever written a function that needs to run 10,000 times with lots of random inputs knows that there's going to be a lot of corner cases and edge cases to defend against. So this is a pretty pared down version of this. But the bread and butter is here, right? You need a first play. You initiate your drive, and then you basically just enter straight into a while loop, and you say that while you haven't turned the ball over and you haven't scored a touchdown, you basically just keep on sampling the new plays by using the old play's ending point as the new play's starting point. And then you just join it, sample it, and you basically rinse and repeat until you break the while loop. So at its core, it's just a lot of joining and sampling, which makes this actually a pretty simple function when you get down to it. And just to give you a flavor of what it actually looks like, you'd start with one play, and then maybe you'd get 2 yards, so you'd sample from 2nd and 8. You end up with a nice play here, and so on and so forth until, in this case, you end up with a long touchdown. And I wanted to highlight these two different sort of sides of this data frame to show that this is the stuff that the simulator cares about, right? This is the thing that it thinks matters, your position, your down, your distance, whether you scored a touchdown. But then if you actually sort of bring in this descriptive data, you sort of understand that we're creating these sort of Frankenstein drives that are blending together plays from all sorts of places. A 2017 Cowboys game or a 2019 Seahawks game. And the quarters jumping around, and these people are not all teammates, but they are for the purpose of our simulation. So you really get an idea of how this function is sort of creating this blend of a bunch of different games. OK, how can we speed it up? Like I said, I got to run this 10,000 times. And when I first built it, it was a case where I would run it before bed, and then when I woke up, I would just pray that my R session hadn't crashed. But that's not really sustainable. And as much as I am a disciple of the Tidyverse Church, and I think that it's made data science accessible and intuitive in a lot of ways that have quite literally changed my career and my life, it's not quite known for speed. And in this case, like I said, all we're really doing is joining and sampling over and over again. So what we can do is we can look for packages that actually specialize in doing this really quickly. So the collapse package has a join function that's pretty fast. The DQRNG package has a sampling function that you can build up a sort of your own sample n function from. I'm not quite sure how these people made these so fast. They're smarter than me, but I get to sort of leverage their discoveries for my own blog posts. And ultimately, it makes a big difference. So we're able to chop down the average runtime of this function by about 50% from 0.4 of a second to 0.2 of a second. If you run it 10,000 times, that makes a big difference. OK, so we're missing these nodes for transition probabilities, but we can go ahead and simulate them and plug them in. And what that means ultimately is that we can collect these probabilities at the end and add ultimate win probabilities for each team. And with this run of this simulation, I ended up with 49.7% for the kicking team and 50.3% for the receiving team. It's a little bit of false precision there in that there's simulation error in here, and there's also potential methodology error if you have gripes about using empirical probabilities here or here, or some of the other assumptions that go in. But ultimately, it's basically a 50-50 proposition. You're not going to be able to mess with these probabilities so much that these ultimate terminal nodes are not going to at least have 48, 49% of probability, which is pretty cool, because the NFL started with a version of overtime that was basically inherently unfair to teams that lost the coin toss. And coin tosses are obviously no reflection of the skill of the team. It's purely random. And they put together a version of overtime that was actually basically completely fair, which is pretty cool. And it basically says that in reaction to the Super Bowl of this past year, even though the 49ers basically got skewered in the media for their decision to receive the ball, they really didn't do anything that was indefensible. Finally, as I've come to learn after years of blogging and publishing my work, you can't convince everyone. Not everyone's going to like my chart. I posted this a couple weeks after the Super Bowl, and I got lots of responses like this that basically said stuff like, stat nerds will waste hours telling you about probabilities, but never factor in the humans involved. So you can't please everyone, especially people that watch sports on television. But I hope that, in this audience and in this auditorium, I'm with people that are a little bit more discerning in their opinions about math and stuff like that. So perhaps you have at least a little bit more mature opinions about this work than others. And if you have questions about the methodology or anything else, I'd be happy to answer questions in the happy hour. Thank you.